One last thing from this problem before we move on is that I forgot to mention that the multiplication rule is for and, right? The probability of E and F. But the thing about and as an English word is that it often hides and masquerades as other words. So for example, in this problem, we had the word all. See that right there? All of them are AAS, which means you want the first one to be AAS and the second one and the third one. So watch out for words like both, all, none, two or twice or three or thrice, those kinds of things, because they're usually hiding an and underneath it, right? If you have all of them, that means that the first one and the second one and the third one. Or if you have none of them, that means the first one is not and the second one is not and the third one is not, things like that. So be careful. Multiplication rules often hide in unsuspected places. In general, if you're talking about more than one thing, more than one graduate, more than one card, more than one whatever, that's usually the multiplication rule. Speaking of which, let's talk about a few free throws. I'm never going to be able to say this correctly. Suppose the average free throw percentage for an NBA player is 77%. So in other words, the chances when they go up to the free throw line that they're going to make a successful shot is 77%. You're going to randomly select 3 random independent NBA players, people that have nothing to do with each other, and have each of them shoot a free throw. So for each player, how many random outcomes are possible? Well, that would be 2, right? So they either succeed or they fail, right? And then what are the probabilities of each one? Well, it says the chances of them being successful is 0.77. So that would be the chances of success, and then the chances of failure would be the complement of that. Oops, I better write that up here. Probability of failure is 1 minus the probability of success, which is 1 minus 0.77, which is 0.23. Okay. It's that complement rule that we learned about in section 5.2 coming back. And just on a side note, and this is going to come back in chapter 6 to a great extent, S often stands for success and F stands for failure. Right? All right, now how large is the sample space? Well, you've got 3 shooters going up, right? So they have 2 options for the first shooter, he could succeed or fail. Then you have 2 options for the next one, succeed or fail. Then 2 options for the third one. That would give you a grand total of 8. 8 possible outcomes for the sample space. All right, now we're going to do something a little bit old school, and we're going to draw a tree diagram for that sample space. So let me do that. 1 second. Poof, there it is. All right, so we have our first player right here in green. Pretend they're wearing a green jersey, and they've got a chance of success or fail. And then the second player wearing a blue jersey comes up, and they could succeed or fail after the first one succeeds. Or if the first one fails, then they could succeed or fail after that. Then the third player is wearing a red jersey, and they could succeed or fail, right? And that gives you 8 options totally. When you count these branches here at the end, you've got 8. So that means our options are succeed, succeed, succeed. That's SSS. Or succeed, succeed, fail. That's SSF. Then succeed, fail, succeed, and so on. All the way down till fail, fail, fail at the very bottom. So there are your options. However, not all these options are equally likely like they were in section 5.1. Section 5.1 is really basic. But these are not all equally likely because our chances of success and failure are not the same. They're not equal. In section 5.1, we assumed 50-50. Right? In 5.1, we said, oh, pretend it's 50-50 every time, right? Heads and tails, males and females, that kind of thing. But in this case, that wouldn't make sense. I mean, first of all, it'd be a pretty terrible NBA player that only has 50% chance of making a free throw. So because of this, the ones that have more S's in them, more successes, should be more likely because S is more likely as a 0.77 chance. Okay, so now we're going to use the multiplication rule to find the probabilities for each possible outcome and construct a distribution of the results at the right. Okay, so let's take a moment and figure those out. 1 second. Let's start with SSS. Oops, you know what, let me fill this out, 1 second. All right, here are all the options. We just listed them above on that tree diagram. So let's find the probability of SSS first. So it's implied in there that you want a success and a success and a success, right? So it's probability of success and success. Hold on. And success. It looks like sand. And success. So this is the probability of success, which was 0 probability of success times the probability of success times the probability of success. And that would be 0.77 cubed, right? Because you're multiplying it by itself 3 times. And 0.77 cubed is 0.77 caret 3. That's what this button is. That's the caret button. And then press 3 and then enter, and you get 0.4565. So there we go. Okay, so now we got to do it all again, but for 2 successes and a failure. So let me do that real quick. Success, success, fail would be I want a success, then I want a success, then I want a failure. So that means I want 0.77 times 0.77, but this time times 0.23. Let me make that very clear. So that means I want 0.77 squared, move my right arrow, or times 0.23. You could use parentheses as well. And we get 136367. Okay. There, I just need to make that a little bit smaller, otherwise I'm going to run out of room here. All right, so that means that this one up here is 0.456533. Oops, I don't know why that's giving me grief here. All right, then this one over here is 0.136367. But there's a couple others that should work the same way. So the one we were looking at had success, success, oops, and failure. Sorry about that, failure. Right here. Okay, so that means that I needed success, success, fail should be here, but it should also be here, and it should also be here, because each one of these had one failure and 2 successes. Let me highlight these ones for you. So let me put them in like a green color so you can see. And this one is going to get orange. It's going to be a very multicolored table here. All right, then what about, actually, there we go. I really color-coded it now. So green for go, success, success, success. That's great. Yellow for slightly cautious, right? You know, it's not doing great, but you're doing okay. Success, success, fail. Then orange for really cautious. 2 failures and 1 success. And red for the bad one. Anti-crafty. Okay, so let's do success, fail, fail. So that means you want a success and a fail and a fail. So you want 0.77 times 0.23 times 0.23. And if you do that, 0.77 times 0.23 squared, that'd be 0.040733. All right, and that's this one. And once you have it here for this orange one, all these orange ones will be the same thing because they have 2 failures and 1 success. And then the last but not least would be the probability of fail, 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 the bad one. So it's the Shaquille O'Neal of this problem because, of course, we all know he was terrible at free throws. So that'd be failure, failure, failure. That would be 0.23 to the 3rd power, which would be 0.23 caret button. That's above your division, 3. Enter. That's 0.012167. And there I got it to go here too. All right, so hopefully that all makes sense, right? You've got your good successes up here with the green. You've got your moderate kind of successes right there with the yellow. That's this one right here. I'll highlight that one for you. Then you got your failures right here. You got to watch out for those. Those are the bad ones. Then you got your orange ones right here, right? That's this group right here. Oops, I think I don't have an orange. Hold on. But I do have a green of some kind. So that's as close as I can get. Sorry about that. But the orange is out of luck. But I really like my idea. Red for stop, red for bad, green for go, and then these are the two levels of caution inside. All right, so now we're going to find the probability that the first two are successful and the third player fails. So we want the first two to succeed and the third player to fail. Well, we actually already found that. That's right here. So first two succeed, third player fails. That's success, success, and then failure. So that's 0.77 times 0.77, that's 0.23, or times 0.23, which is 0.136367. So we already did this one. Already found above. Okay, now we're going to find the probability that two succeed and one fails. And notice these are not the same question. But those questions aren't F and or G and H, they're F and G. F and G, sorry about that. So F and G are not the same. Now what's the difference? Well, because F is talking about the first two succeed, the third player fails. G is talking about any two of them succeed. So this is the probability that any two succeed and one fails. So that means that you're really finding the probability of several things. You could say that's SSF or SFS or FSS, right? Because that'll give you two successes and one failure. In other words, I'm trying to add up all my yellow ones, right? Instead of just one yellow one, I want all of them. Okay, so if I'm going to do that, let me find that out. One second. Okay, so we found out one yellow one is 0.136367. So let me write that out. So it's 0.136367 plus, and then the next one, 136367, but you're adding them this time. You're not multiplying because it's an OR problem. OR means you get to add. And would mean that you multiply. So up here, when I was just doing SSF, right here, I want the probability of the first one succeeding and the second succeeding and the third one failing. So I multiply. But down here for this one, I want either SSF or SFS or FSS. So I want to add those probabilities. And that would give me a grand total of, let me grab this, 0.136367 plus 0.136367 would be this. Or if you like, you could say 3 times 0.136367 because that's what multiplication is. It's adding up. So it's 0.409101. Oops. And there we have it. And you'll notice that you got to be careful in probability because those two questions appeared very, very similar, but they are not the same. And that's my warning to you here down at the bottom of this page. You have to be cautious because this one was talking about one particular one of the yellow ones, and this is talking about all three of the yellow ones added up. And it was all based in this English right here. Two succeed and one fails, that's this. First two are successful and the third one fails, that's SSF in particular. So this one is SSF in particular. This one is any two S and one F. And it's all based in the English. So you've got to be super, super, super cautious when you're reading the wording of these problems.